Hi, welcome back to this video series on program synthesis. Today I'm going to talk about a fundamental problem. We discussed about adding two unsigned numbers and handling overflow. Today I'm going to talk about handling the signed integers. Okay, suppose I have two numbers x and y, and the numbers can be positive, negative, equal to 0, whatnot. So how do I check whether I can perform x plus y safely? Okay, meaning without creating integer overflow problems. Okay, I just want to check whether I can add them without creating problems. Okay, so first of all, I want to convince you that in computer arithmetic, when you add two numbers, the result may not fit the available memory. That means you'll have to throw away some bits. Therefore, the answer x plus y may be counterintuitive. Okay, for example, adding 3 to 1 is usually 4 in our regular math, but it can be -4 in computer arithmetic when we assume our numbers x and y are just say 3-bit numbers. Okay, so we have a clock like this, almost a clock. We have 0, 1, say 2, 3, and we can't represent 4 because 4 requires, okay, what is the binary representation of 4? 4 is 100, right? But we have to reserve the most significant bit for handling negative numbers. So we can't represent 4, unfortunately, only with 3 bits in the negative case. Therefore, we have to say this is -4, and then -3, and then -2, okay, and -1. So this is what happens when you create a declaration like int x in the C language. Okay, of course the C language allows you to have much bigger clock than just a 3-bit clock that you're seeing. In the C language, integers usually in many modern machines 32-bit. Okay, so you can imagine that the most significant bit is the signed bit and the rest are all the data bits, right? So this is the model followed in computers. Okay, so the question now is, given two numbers x and y, how can I check whether I can add them safely without getting into this trouble that I'm just showing you here? This is the trouble part, right? 3 plus 1 is -4 is a trouble. So I want the computer to synthesize a program for me. Using program synthesis technique, I'm going to synthesize an algorithm that will tell me whether I can add two numbers safely. Okay, so I'm going to show to you how we can use program synthesis for that particular purpose. Okay, so let's get started now with program synthesis. So what you're going to see is, in my previous segment, I talked about basic utility. For example, an utility that will help me to detect whether two numbers are same sign, meaning both of them are positive or both of them are negative. So one is positive, one is negative, that kind of combination, it will tell us. For example, we just run this synthesizer that's going to tell me an algorithm that will help me to detect whether number x and y are both positive or negative or whatnot, right? So this is already given for us. We have synthesized it from the previous session. Actually, we can leverage this synthesis model and use this to derive a new program that will help us to check whether two numbers can be added safely. Okay, but if you notice the definition, it uses left shift not XOR, and then it is going to throw away 3 bits, right? I'm working with only 4-bit representation. So if you have a 32-bit representation, you will be throwing away how many? So for 4-bit, you're throwing away 3. That means for 32-bit, you will be throwing away 31 bits. Okay, anyway, you can easily generalize this model for detecting whether two numbers are the same sign or not. So I'm going to copy and paste this and use this for checking whether two numbers can be added automatically, right? So I pasted the same sign function. Actually, I don't have to use this. I can directly use the raw low-level syntax like bitwise add, XOR, not, and so on. But it will be helpful to make use of whatever we synthesized earlier, right? So why not just plug in same sign function that we already know that is helpful. So let's see whether synthesizer will come up with a program for us. The program is based on learning by example model. I didn't specify what is the meaning of 2's complement addition, what does it really meaning of overflow, underflow. I didn't say that. I just give some examples. Like for example, I said here, of course, adding x and y is same as adding y and x, commutative. The rest you're seeing is I'm adding, this is 7, right? I'm adding 7 with 1, okay? So the answer is -8 in 4-bit representation, okay? You can't represent 8 in 4-bit representation in 2's complement. So I put 0 wherever there is overflow, I put 1 wherever there is no overflow, okay? So I'm going to give these many examples and see whether the synthesizer can come up with something meaningful for us, okay? That's what I'm going to do. So I'm going to now straight away run this and see whether we can quickly get the program that will help us to check whether 2 numbers can be added safely. While it is synthesizing, I must show you when does overflow happen, when does underflow happen, and then we can talk about it once. Yeah, okay, I got the output also in the meantime. So the program has been synthesized. This program will help us to decide whether 2 numbers x and y can be added safely without creating integer overflow problems. Okay, here is the logic behind this program. So we take our x, right? This is the number x as an input, and okay, let me write it here. So what are we trying to do? We create. So let me explain the syntax in a more regular way. So we have number x, right? And we have here we are doing x plus y. So we are calling the same sign function for this particular pair, right? We ask whether x and x plus y has the same sign, meaning if x is positive, x plus y is also positive, and if x is negative, x plus y is also negative, that kind of thing. That's what the same sign detector is supposed to do, which we already synthesized. So this is the same sign function. So we are calling it on x and x plus y. And then we are also doing again for x and y, okay? And then we have another call to same sign function, okay, for x and y. We check whether both x and y are same sign or not. Okay, so what is the next thing we are doing? Remember, same sign function returns 0 or 1. It returns 0 when they are not same sign. It returns 1 when they are same sign, okay? So now we take these 2 data, right? This could be 0, 1, this could be 0, 1, right? And then we are doing bit greater than or equal to, okay? So we are checking whether this is greater than or equal to this. So why would this be correct? Okay, why would this is good enough for us to decide whether 2 numbers x and y can be added safely? Well, let's consider this a few scenarios now. Okay, let this code be here. Let me go back to the whiteboard and show you when will overflow happen. Okay, this is 3-bit representation now. Let's just understand. If you add 2 positive numbers, say 3 and 2, yeah, overflow happens right away, right? 3 plus 2 is 5, which means it's -3, okay? So on the clock, we can go clockwise for addition and anti-clockwise for minus, right? So 3 plus 2 means take 2 steps from 3, we end up with -3. That means we started with 2 positive numbers and we end up in a negative number. So overflow happens there. Let's consider the other scenario. Let's take -4 and -1. Okay, what is -4 and -1? Is -5. But -5 is not possible here, right? Which means we end up with 3. Okay, basically from -4 you go 1 step anti-clockwise, so end up at 3. So we got another scenario. We started with 2 negative numbers and the answer is positive. Okay. So what about mixed case? Let's take x to be greater than or equal to 0 and y to be less than 0. Say, for example, x to be 3, y to be -4. So what is the answer? Well, the answer is -1, which is perfectly fine because we have it here, and which is meaningful, right? 3 minus 4 is -1. Take any 2 numbers, -3 and 2, -1. It's perfectly fine. Take 1 and -1. Well, it's 0. So any combination that you take when the signs are opposite, no problems, no underflow, overflow problems. So problems happen only when x and y are both positive, or when both x and y are both negative, meaning if they are same sign, then overflow can happen. Okay. So in that case, as you can see here, adding 3 plus 2 resulted in 5. 5 doesn't exist. We actually end up with -4. Okay. How did we get but not 1 minus 4, sorry, you end up with minus 3. 3 plus 2 is 5, right? So you're at 3, you take 2 steps. How did we reach minus 3? We can actually mathematically summarize. When you add two numbers, x and y, if they overflow, so what you actually do is you take 2 power w, the word size, which is 3-bit in this case, right? And then you basically compute the difference between these two. So I must have written this here. X plus y minus 2 power w, right? Say 2 plus 3 is 5, but 5 is not possible, right? 5 is nothing but minus 3, which you can get it from 5 minus 2 power 3. 3 is the word size, in this case, the 3-bit number, so which is minus 3, right? And the same thing you can apply. Let's take 3 plus 1. 3 plus 1 is 4. 4 minus 8 is minus 4. So we are here. So it works. So this is the model. Usually this is the model we use when there's overflow. Okay. So as you can see, the problem happens only if your types are the same sign. Okay. Now with that background, we can go back to the model that was synthesized and reason about it. Okay. So let's assume x and y are both greater than or equal to 0. So in that case, the same sign here will return 1, right? And let's assume x and y, when we add, there is no overflow, okay? Just for a moment. In that case, the same sign of x matches with the x plus y. So basically, you have same sign on both sides. So your model looks like this, right? You have your x plus y. You're checking whether it's the same sign or not, and then you're checking against x and y, same sign, right? That's what you're doing here. So I'm not writing the function name. It's basically calling to same sign function. Yes, as I call it short form. Okay, let's see. Does it make sense now? If x and y are positive numbers and they don't overflow, of course, then they both have the value 1 and 1. 1 greater than or equal to 1 is true. The answer is 1. So perfect. What about the other scenario? Let's consider the scenario that x plus y overflow happened, okay? And if that happens, this will be 0 because overflow happened. And this will be 1. 0 greater than or equal to 1 is wrong, so you get a 0 as output. Okay, so there you go. So this program, you can try other combinations yourself. Will help us to detect whether two numbers can be added safely or not. So that's basically the idea. So let me quickly go to the program, that the code, and I will explain the grammar a little bit. What did I do? I used the already synthesized function called same sign, because my intuition was telling me that same sign will be helpful to detect whether two numbers can be added or not. Therefore, I plugged it in here like same sign. We don't need this constant. Okay. And we were able to just apply same sign function. That's basically it. And of course, this Boolean to bit vector, I talked about it in my previous videos. If you have a Boolean type, you need to convert it to bit vector. Otherwise, you cannot combine Boolean and bit vectors. Okay, so that's basically it. And I have given some examples, assuming that the examples are a good collection of examples covering different aspects of your program that you're synthesizing. You can avoid the specification problem as much as you can by training the system with examples. All right, that's basically the purpose of showing you how to synthesize a program that will help us to detect whether two numbers can be added safely, two's complement numbers. Okay, thank you for your attention.